There's this huge sphere of nothing out in deep space. It's called the BOOTES void. Astronomers call it the Great Nothing. It's about 330 million light-years across. And it's making scientists rethink the rules of the universe. How can something that empty exist in a cosmos built by gravity? Is it just a rare accident? Or is it a sign of physics we haven't discovered yet? And what does that kind of nothingness make you wonder about where we are? For most of human history, the universe was a flat sheet. Stars were just points of light on a dark canvas. But then, with new tools, astronomers could look deeper. They could measure not just where a galaxy was, but how fast it was moving away. That measurement is redshift. It became a kind of cosmic ruler. Scientists like Robert Kirshner and his team used it. They built the first true three-dimensional maps of the universe on the largest scales. They weren't just plotting dots, they were seeing the architecture, and what they expected to find was a cosmic foam, a relatively even mix of galaxy clusters and empty spaces, all shaped gently by gravity over billions of years. But the reality they began to chart was different. It was far more dramatic. It was a vast cosmic web, a delicate lattice of brilliant filaments where galaxies gathered, and between them, these immense, dark bubbles of near nothingness. This web is the large-scale structure of everything, and inside this newly mapped territory, they found a blank spot. But this wasn't just any empty bubble. It was a staggering absence, the BOOTES void. It's so enormous that if you put our Milky Way at its center, the next major galaxy would be tens of millions of light-years away. In every direction, you could fit thousands of galaxies like our own inside this sphere of emptiness, with unimaginable stretches of dark, quiet space between them. Finding it was like a mapmaker charting all the continents and oceans of Earth, and then discovering a previously unknown expanse of open ocean, so vast it could swallow the entire Pacific. This wasn't a small gap in the data, it was a fundamental feature of the cosmos, one their theories struggled to explain. Gravity is the force that builds the universe. It pulls matter together, it creates clusters, it forms filaments, but according to the standard models of the time, it does not create voids of this staggering scale. The very existence of this great nothing posed a quiet challenge, a profound one. It whispered that the story of how the universe arranged itself might have chapters we hadn't even begun to read. In the early 80s, Robert Kirshner and his team were mapping the cosmos. They were working in BOOTES, the herdsman, counting galaxies, measuring their light, plotting where everything was. But the data started to form a pattern that didn't make sense. The numbers didn't add up. Their models said there should be galaxies, a good scattering of them. But their instruments found silence. The counts weren't just low, they were dropping almost to zero. In 1981, they published a paper. The title was "A Million Cubic Megaparsec Void in BOOTES." And they put a question mark at the end. That mark was everything. It was their own doubt. The finding was so extreme, so against what they knew about gravity building the universe, that they thought they had to be wrong. Maybe the telescopes weren't good enough. Maybe dust in our own galaxy was in the way, creating an illusion. Other scientists felt the same. It had to be a mistake, an artifact in the data. The model back then was like Swiss cheese. It had holes, but they were small, scattered through all the galaxies. What Kirshner's team was seeing wasn't a small bubble. It was a cavern, a chasm. To prove it, they had to rule everything else out. They needed more observations. They used bigger telescopes, better instruments pointed at the same dark patch. They looked in different kinds of light, searching for any hidden mass. It was slow work, and with each new look, the result got harder to deny and more unsettling. The galaxies just weren't there. Kirshner remembered that moment later. He said, "We kept looking and the galaxies just weren't there. a quiet statement. This wasn't an error, this was a feature of the universe. The BOOTES void did more than add an oddity to the books. It challenged the comfortable model. It said the holes in the cosmic Swiss cheese could be vast, big enough to swallow whole superclusters. It raised a question. If gravity shaped everything, what kind of force could carve out a sphere of nothing, hundreds of millions of light years across? The great nothing wasn't a maybe anymore. It was a fact, and its silence needed an explanation. 700 million light years from here, in BOOTES, there's a sphere of space. It's so large it's hard to even picture. First, you have to imagine the distance light covers in a year. Light moves at 186,000 miles per second. Multiply that journey by 330 million. That's the diameter of the BOOTES void. To put it another way, if our Milky Way galaxy was the size of a grain of sand, the void would be a hollow sphere over 6 miles wide. And inside that sphere, the next grain of sand would be tens of millions of light years away. It's an emptiness that's almost impossible to grasp, but then the story shifts. The BOOTES void isn't a perfect vacuum. Careful surveys have found galaxies inside it, about 60 that we know of. 60 galaxies sounds like a lot. But then you remember the scale. A typical region of space that large should have thousands of galaxies, tens of thousands. Finding only 60 is like exploring a city built for millions and finding just a few small towns miles apart. The silence is overwhelming. Astronomers call it an underdense region. The average density of matter there is just a tiny fraction of what it should be. That extreme sparseness makes it a profound statistical outlier. According to our models of how the universe evolved, a region this empty shouldn't exist. Gravity acts like a universal glue. Over cosmic time, it pulls matter together. It should have drawn that sparse material into more galaxies or pulled more galaxies in from outside. The fact that it didn't, the fact this great nothing persists, tells us something critical. Either our understanding of gravity on the largest scales is incomplete, or something happened in the very early universe to create this staggering emptiness on purpose. The scale of the void isn't just a measurement, it's a question. Written in the dark, the cosmos has a structure. It's called the cosmic web. It's not just galaxies scattered around, it's more like a giant three-dimensional spiderweb. At the knots where the strands cross, you get these brilliant clusters, thousands of galaxies packed together. The strands themselves are filaments, long, thin lines of galaxies. Like pearls on a string, and in between these bright structures you have the voids, the great dark spaces. They're like the bubbles in a foam, or the empty chambers in a vast cathedral. All of this came from a very simple beginning. Right after the Big Bang, the universe wasn't perfectly smooth. There were tiny ripples, quantum ripples in the density. Imagine the surface of a pond, but on a scale smaller than an atom. Gravity worked on those ripples for billions of years. It sculpted them. Places with a little more density pulled in more matter. They grew. Those denser patches became the seeds for the clusters and the filaments. The emptier patches got left behind. They expanded as the universe expanded. They became the voids. Gravity alone creates this web. You can see it in computer simulations. They show the universe evolving from a faint haze into this intricate lattice, with dark bubbles inside it, so the voids aren't mistakes. They're an essential part of the structure. They're the expected counterpoint to the crowded filaments. A typical void might be 100 million light years across. Its walls are made of galaxy filaments, maybe a few galaxies drifting inside. It fits the model. It follows the rules of gravitational collapse from those initial random seeds. Then there's the BOOTES void. If the cosmic web is a collection of soap bubbles, BOOTES isn't a bubble. It's a cavern. It's so large and so empty that it strains the explanation. It pushes against the idea of simple random chance followed by gravity. When you see the predictable structure of the cosmic web, the strangeness of this great nothing comes into focus. It's not just part of the pattern, it's an outlier. It seems to question the pattern itself, the lambda cold dark matter model. It's our main picture of the universe. You take the laws of physics, the starting conditions, and you run the simulation forward, billions of years, and it works. It builds the cosmic web. Filaments, clusters, and the voids, but the voids it makes, they follow a pattern, a range of sizes, a statistical expectation. The BOOTES void doesn't fit. It's an outlier, so you go back to the beginning. The early universe was nearly smooth, almost uniform, but with tiny ripples in density, random fluctuations. Gaussian fields, they were the seeds. Gravity pulled on them. Denser spots became clusters. The emptier spots became voids, and those initial ripples, they had a distribution. Most regions were average, some were a bit more or less dense. Extremes were possible but unlikely. The more extreme, the more unlikely. It's like dice. Rolling a 7 is common. Snake eyes is rare but possible. Now imagine rolling snake eyes over and over, dozens of times. That's the BOOTES void. In statistics, they measure this in sigma. Standard deviations from the average. A 2 sigma event is unusual. 3 sigma is very rare. The BOOTES void has been placed at 3, maybe 4 sigma. The chance of it forming from those random beginnings is incredibly small. It's not impossible. In a vast universe, rare things occur, but its existence presents a choice. Is it just a fluke, a 1 in a billion roll of the dice, or is it a clue that our blueprint is incomplete? Maybe the seeds weren't so random. Maybe something else carved out that emptiness. On purpose, perhaps the great nothing is a scar from before time began. To get there, you have to go back to the very first moment, a fraction of a second so small it's hard to even describe. That's the era of cosmic inflation. The leading idea is that space-time itself went through this burst of expansion. It took a region smaller than a proton and stretched it to something bigger than everything we can see. That process smoothed everything out, and it planted those tiny quantum ripples, the ones that would later become galaxies. Inflation ended when the field driving it, the inflatoned field, decayed. That decay released a huge amount of energy. It filled everything with a hot soup of particles. Everything came from that, but what if that ending wasn't neat? What if it was messy, uneven? There's a model called eternal inflation. In that picture, inflation doesn't end everywhere at once. It stops in patches. Like bubbles forming in a boiling pot, each of those bubbles becomes its own universe, with its own laws of physics. They all expand inside a bigger, eternally inflating multiverse. Our entire cosmos, everything we see, might just be one of those bubbles. Now imagine 2 of these universe bubbles, expanding in that primordial froth. They grow, they eventually meet. When they collide and merge, the boundary between them is a region of incredible energy, chaos. The physics at that collision wall would be unlike anything inside either bubble. That violent merger could have swept the region clean. It might have smoothed out those density ripples, the very seeds for future galaxies, leaving behind a vast, barren patch in the infant cosmos. As our universe kept evolving and cooling, this scar would remain, a fossilized imprint of that ancient collision, stretching with the expansion of space itself. Into the staggering emptiness we see today. In this idea, the BOOTES void isn't a fluke. It's a direct prediction, a relic from the multiverse. It's a bridge between the physics of the unimaginably small, quantum fields and inflationary energy, and the structure of the unimaginably large. If it's true, then when we point our telescopes at that dark patch in BOOTES, we aren't just looking at an absence. We're looking at a shadow on the wall of our cosmic bubble, a whisper from the moment our universe was born. Gravity built the universe, but it might also be the most efficient way to tear it down. That idea changes the BOOTES void. It's not a static scar, it's a process, it's something that's still happening. The great nothing wasn't born empty. It was made empty. The theory says that long ago, a truly colossal supercluster sat at the heart of this region, a gravitational titan. Over billions of years, its immense pull acted like a cosmic drain. It started to attract everything around it. Galaxies from the void's interior were slowly tugged inward. Matter from the surrounding filaments was siphoned toward this growing behemoth. The process wouldn't just pull galaxies in, it would accelerate them. As they fell toward the center, they would gain speed. They'd leave behind more and more empty space. Eventually, the drain would finish its work. The central supercluster, having consumed everything, might itself have merged into the surrounding cosmic web. And that would leave just a vast, drained basin behind, a gravitational sink. If this happened, it would leave a specific mark on the sky. The theory predicts a shell. A ring or a wall of galaxies around the void's outer edge, like the raised rim of a crater. These would be the galaxies that were once falling inward, now slowed and collected at the perimeter. Or galaxies from outside that were pulled toward the basin but never quite made it in. So, do we see a shell? The evidence is interesting. It's not definitive yet. Surveys show the few galaxies inside the BOOTES void aren't randomly scattered. They seem to align in a loose, tube-like structure, and the void's boundaries aren't perfectly smooth. There are hints of denser walls. It's like we're looking at the faint, weathered remains of that crater rim. The dynamics are fascinating because they use gravity's known rules to explain an extreme outcome. Gravity doesn't just build, it also clears. It organizes matter into dense knots, and in doing that, it can create corresponding deserts. Think of a mountain range pulling moisture from the air. That creates a rain shadow, a desert on the other side. The supercluster was the mountain. The BOOTES void is the rain shadow. This idea reframes the void completely. It's not a mysterious blank from the beginning of time. It is a consequence, a monument to consumption on a cosmic scale, carved by the same gentle force that keeps our feet on the ground. It turns the great nothing into a story of transformation, where emptiness isn't the starting condition, it's the final result. The void might not be a scar or a drain, it could be a note, one deep, resonant note left over from the first sounds the universe ever made. To get that, you have to go back to the beginning. For the first few 100,000 years, the cosmos wasn't clear. It was a hot, thick fog. A plasma of particles and light all tangled up. In that dense medium, gravity tried to pull matter into clumps. But the radiation pressure pushed back. That created a tug of war, a push and pull that sent spherical pressure waves rippling out through the primordial soup. Like sound waves moving through air, those are the baryon acoustic oscillations, the cosmic equivalent of a ringing bell, and they left a permanent mark. When the universe cooled enough for atoms to form, about 380,000 years after the Big Bang, the light finally broke free. That moment is the cosmic microwave background. The afterglow, but the matter was left behind, frozen in place. Those sound waves stopped. They left a characteristic imprint, a preferred scale. Think of it like dropping a pebble into a still pond. You see ripples expand in perfect circles. Now imagine the pond instantly freezing solid the moment the first ripple reaches a certain distance from the center. That frozen ripple is the imprint. In the cosmos, that distance is about 500 million light years. It becomes a standard ruler woven into the fabric of everything. When we look at galaxy surveys now, we can still see this echo. Galaxies are slightly more likely to be found at a specific separation from each other. That separation matches the frozen ripple. It's a fundamental harmonic of the young cosmos. Now, the BOOTES void. Its diameter is about 330 million light years. That's intriguingly close to the scale of those primordial sound waves. Could the void be the ghost of a single, extraordinarily deep trough in one of those waves? If the initial density fluctuation was a profound low point, a deep valley in that early landscape, it would have expanded with the universe. As space itself stretched, that valley would have grown into a vast underdense region. A bubble of silence where the wave's low pressure cleared matter away. In this view, the great nothing isn't an accident or something built later. It's a fossilized echo. A single, frozen note from the universe's first symphony. It offers a direct link to those earliest moments, a region of space you can point to and say, that emptiness was set in motion before the first stars ever shone. It reframes the mystery from a statistical fluke to a potential key. If the void scale truly aligns with that fundamental harmonic, it becomes a powerful calibration point. A way to test our understanding of those first vibrations with new clarity. It turns an absence into evidence, the silence into a song. But what if the emptiness itself is the force? The universe isn't just expanding, it's accelerating. Something is pushing everything apart faster and faster. We call that dark energy. It's the dominant thing in the cosmos now. About 68% of everything, and we know almost nothing about it. The standard view is that dark energy is perfectly smooth, a uniform hum, the same everywhere. That's the simplest explanation, but what if that's wrong? What if dark energy has texture, lumps and bumps, variations in its strength across space? It's a speculative idea, but it suggests that in the distant past, the region that became the BOOTES void might have had a stronger dose of this repulsive force. Think of two balloons inflating side by side. One has a normal pump, the other has a more powerful pump. That second balloon expands faster. It stretches its rubber thinner more quickly. If that balloon was a region of the early universe, that accelerated expansion would have a dramatic effect. It would dilute the matter inside it more efficiently. Those tiny density ripples, the seeds for galaxies, would have been stretched apart before gravity could get a grip. Galaxy formation would have been stifled almost from the start. The result would be a vast, underdense bubble, a region cleared out not by gravity pulling things away, but by space itself pushing outward with extra vigor. So in this idea, the BOOTES void isn't a relic or a sink. It's a fossilized imprint of dark energy's uneven hand, a place where the rules of expansion were written differently. This connects the void directly to the greatest puzzle in cosmology. If it's true, these voids are not just curiosities, they are unique laboratories. By studying their size, their shape, the few galaxies inside them, we might detect the faint fingerprints of variable dark energy. We could learn if this force behaves the same everywhere or if it has a geography of its own. It turns an immense absence into a potential key. A silent, dark expanse becomes the most sensitive detector we could imagine for probing the force that will decide the fate of everything. Empty space isn't really empty, not at the smallest level. In the quantum world, there's no perfect stillness. Even a total vacuum is active. It's a kind of seething foam. Pairs of virtual particles appear, they borrow energy from space itself, and then they vanish almost instantly. That's the quantum fluctuation. It's the background hum of everything. And our theories say this is where everything we see comes from. During cosmic inflation, those tiny quantum ripples got stretched to enormous sizes. They were frozen into space-time. They became the slight differences in density. And later, gravity used those differences. It sculpted them into galaxies, into clusters, into the whole cosmic web. That's the standard story. But what if in one patch of that quantum foam, the fluctuation wasn't just a ripple? What if it was something bigger? Imagine a single, exceptionally large fluctuation, a negative one, a deep dip in the energy field, a trough of nothingness deeper than the rules usually allow. It would be a rare event, like a die landing perfectly on its corner. But in the infinite churn of the quantum realm, even the most unlikely events can happen. They do happen. If such a wild fluctuation happened in the patch of space that would become the BOOTES region, its fate was set from the very first fraction of a second. This patch started with a deficit, a deeper silence at its core. Then inflation hit, and inflation acted like a cosmic magnifying glass. It took that microscopic quantum dip and stretched it across hundreds of millions of light years. The deficit was amplified into a staggering void. So in this idea, the great nothing isn't from later dynamics. It's not from a collision or a sound wave. It's the direct macroscopic imprint of a single, improbable quantum event. It's a cosmic scale fossil, a fossil of the universe's inherent randomness. This idea connects things. It connects the two most extreme scales of reality, the bizarre, probabilistic rules for particles smaller than an atom. They are directly linked to the largest structures in the cosmos. The emptiness of the BOOTES void, in this view, becomes a permanent monument, a monument to chance, a scar written into the universe by quantum uncertainty. It means when we look out at that vast dark sphere, we're not just looking at an absence of galaxies, we're looking at the amplified ghost of a particle that almost was. A whisper from the quantum vacuum, a whisper magnified to a cosmic scream. It reframes the void. It's not a puzzle to be solved. It's a signature of the universe's deepest nature. There's another possibility. It's far outside the standard models of physics, a thought experiment from pure speculation. What if the BOOTES void isn't natural? What if it's a work of cosmic engineering? On the Kardashev scale, a Type 3 civilization has mastered the energy of its entire galaxy. Their capabilities would be beyond our imagination. The classic idea is a Dyson sphere built around a star to capture its light, but a truly advanced civilization might think bigger, much bigger. Could they build something on the scale of a galaxy? Or a cluster of galaxies, a structure so vast it blocks the light of millions of stars from our view. From our perspective, that region would just go dark. It would appear as a void. This idea is a staggering leap. It lacks any direct evidence. It sits firmly in science fiction, but as a mental exercise, it serves a purpose. It forces us to confront the limits of our perspective. When we see something as strange as the great nothing, our minds search for a cause, a reason, a purpose. The idea of a cosmic architect is a deeply human response to that scale of emptiness. It turns a cold statistical anomaly into a story, a narrative with intention behind it. Yet this is where science provides guidance. A captivating story isn't enough. Extraordinary claims demand extraordinary evidence. And for the megastructure hypothesis, that evidence doesn't exist. The observed properties of the void, while extreme, can still be discussed within cosmology and physics. They challenge those models, but they don't shatter them. This speculative journey highlights a point about how we explore the unknown. Our curiosity will always leap ahead of our data, painting pictures of wonders and intelligences beyond our own. That imaginative drive is what propels us to look deeper, but the discipline of science is what grounds us. It ensures we distinguish between a beautiful story and a testable truth. The BOOTES void remains a mystery of natural origins, but in daring to ask the wildest questions, we define the boundaries of what we're willing to learn. Mapping a hole in space, it's not like you can just point a telescope at nothing. The problem with the BOOTES void is that you're studying an absence, so astronomers have to map everything around it. They build a three-dimensional census of the cosmos just to define the edges of the emptiness. The main tool for that is the Galaxy Redshift Survey. You capture light from millions of galaxies and you measure a key property. As the universe expands, it stretches light waves. It shifts them toward the red end of the spectrum. Greater redshift means the galaxy is farther away, its light has been traveling longer. So by measuring redshift galaxy after galaxy, you can plot their positions in 3 dimensions. It's cosmic cartography on the grandest scale, but when you survey the BOOTES region, the data tells a strange story. The map doesn't fill in. Instead of a healthy scatter of points, you get this giant spherical gap. The few galaxies you do find are like lonely islands in an ocean of dark, and that creates a puzzle. Is this a true void, or could it be an illusion? One major hurdle is our own cosmic backyard. Our view of the universe is filtered through the plane of the Milky Way. There are clouds of interstellar gas and dust. That dust can obscure light from distant galaxies, so a region might look empty when it isn't. Ruling that out means looking in multiple wavelengths, infrared to radio, to see if the galaxies are truly missing or just hidden. Then comes the statistics. Proving a void this scale requires immense surveys, huge swaths of the sky to incredible depths. Projects like the Sloan Digital Sky Survey have been instrumental. They catalog millions of objects to build our modern map of the cosmic web. But even with that data, confirming the BOOTES void's extreme nature is painstaking. It's counting and probability, comparing the sparse number of galaxies found to the thousands you'd expect. The future of this search is about to get an upgrade. The Vera C. Rubin Observatory, with its immense mirror and giant camera, will begin the legacy survey of space and time. It'll scan the entire southern sky repeatedly over a decade. Deeper and fainter than ever before, it will likely find many more of the faint dwarf galaxies that current surveys miss, and that presents 2 possibilities for the great nothing. The Rubin data could reveal the void isn't quite as empty as we thought. It might be populated by a thin haze of previously invisible small galaxies. Or it could do the opposite. It could confirm the void's stark emptiness with even greater, more unsettling precision. Either result would be a step. We'd either be looking at a slightly more populated, but still profoundly lonely expanse, or we'd be staring into a deeper, more confirmed abyss, making the mystery of its origin even more pressing. Studying nothing, in the end, is a way to understand the everything around it. There are a few points of light in the BOOTES void, not many, but they're there. Galaxies drifting in that cosmic ocean, they're the loneliest places you could imagine, and to understand the void, you have to look at these isolated survivors. What it's like to be a galaxy in the great nothing. There's a spiral galaxy, for example, called MCG plus 0152015. It floats in the void. Millions of light years from its nearest major neighbor. Its existence is a study in cosmic solitude. Now, in the crowded filaments of the cosmic web, galaxies live chaotic lives. They're constantly tugged and pulled by the gravity of their neighbors. They collide, they merge, they rip each other apart in these spectacular dances that trigger bursts of new stars. That environment, that constant interaction, is what shapes most galaxies. It drives their evolution, but a galaxy in the void experiences none of that. It grows up in profound quiet. With so few neighbors, there are no major mergers, no dramatic gravitational encounters. Its evolution is dictated almost entirely by its own internal processes. The gas inside it just slowly cools and forms stars at its own unhurried pace. And this isolation creates a kind of natural experiment. It lets astronomers ask a fundamental question. What does a galaxy look like when it's left entirely alone? Without the violence and chaos of a crowded universe, does it become something different? One possibility is that these isolated galaxies become red and dead. They use up their reservoir of star-forming gas, and with no fresh gas funneled in from cosmic collisions or intergalactic streams, the star formation just stops. The galaxy ages into a quiet, elliptical retirement populated by older, redder stars. Another possibility is the opposite. The void could preserve a kind of cosmic innocence. A spiral galaxy there, untouched by mergers, might maintain its elegant structure for billions of years longer than its cousins in the clusters. It could be a pristine, undisturbed relic of an earlier era, its spiral arms slowly turning in the dark. So studying these lonely islands gives us a control group. By comparing a void galaxy to one from a dense cluster, we can isolate the effects of environment. We learn what's inherent to a galaxy's own nature and what's imposed on it by the bustling cosmic city it lives in. This turns the BOOTES void from a mere absence into a unique laboratory. Its emptiness is the condition that makes the experiment possible. The few galaxies within it aren't just curiosities. They're vital clues. They tell us about the life cycle of galaxies when the noise of the universe is turned down to a whisper. In their solitude, they hold a quieter story about how the cosmos builds itself. The cosmic microwave background is the oldest light we can see. It's this faint, nearly uniform glow across the whole sky. A snapshot from when the universe was 380,000 years old, and it's incredibly smooth for the most part. But when they made these detailed maps of the radiation, they noticed something. A patch in the constellation Eridanus was slightly cooler, just a few millionths of a degree cooler, but it was significant. They called it the CMB cold spot. And it's one of the biggest anomalies in cosmology. It led to a question: could this cold spot be a shadow from the BOOTES void? The idea depends on an effect. The integrated Sachs-Wolf effect. Think of a photon from that ancient light. It's been traveling for over 13 billion years, and for most of that, it's moving through expanding space. Now imagine it enters a huge region, a void, a place with very little matter. In there, space expands a bit faster because there's so little gravity holding it back. It's a tiny difference in the expansion rate, but as that photon travels through, it has to climb back out. And climbing out of a region that's expanding faster than average takes energy. The photon loses a little energy, and for light, losing energy means shifting to longer, redder wavelengths. For the cosmic microwave background, that means a slightly cooler temperature. So if the BOOTES void is along our line of sight to the cold spot, it could, in theory, cool that ancient light. The void's emptiness could be imprinted on the first light. It's a breathtaking idea, a direct cause and effect, a structure that formed later, leaving a mark on light 10 times older, but the pieces don't fit perfectly. The cold spot and the BOOTES void aren't in the exact same place. Their scales are different, and studies show the void probably isn't big enough or empty enough to explain the whole temperature dip. There are other explanations. It could be a statistical fluke or something more exotic, like a collision with another universe during inflation. The debate is still going. But the possibility remains. It changes how we see the cosmos. It suggests the universe isn't just separate eras. The ancient and the modern are connected. A structure that took billions of years to form might be reshaping light that's much older. If it's true, then the BOOTES void isn't just an empty place we look at. It's an active lens filtering our view of cosmic history. Its great nothingness becomes the filter for the first dawn. The great nothing feels like a one-of-a-kind thing. But is it? You have to look at the wider map, and when you do, you find that the BOOTES void has rivals, other giants. There's the giant void in Cain's Venatici. That was found in the 80s. It's about 500 million light-years across, so it's even bigger than BOOTES. And then there's the KBC void, named for the astronomers who proposed it. That one's interesting because we might be living in its outer edges. It's a proposed spherical underdensity, a bubble about 2 billion light-years wide. If it's real, then our Milky Way isn't in an average neighborhood. We're in a slightly sparser suburb of this huge, mostly empty structure. Finding these others changes the question. Is BOOTES a unique monster, or is it part of a pattern? A single fluke can happen. In a vast universe, one extreme thing is possible, but multiple flukes at a similar scale that starts to look like a trend. It suggests our models might be systematically underproducing these colossal empty regions. Our simulations make voids, sure, but they rarely make voids this vast. And this empty, the existence of several supervoids points to a gap. Maybe the initial conditions of the universe had more extreme low-density fluctuations than we've accounted for. Or maybe a process like faster expansion in these regions driven by early dark energy carved them out more efficiently. By comparing these giants, you look for clues. In their shapes, are they all perfect spheres or are some elongated? Their walls, are they sharp or fuzzy? How many galaxies are inside them and what kind? Each detail is a piece of the puzzle. If they share a family resemblance, it strengthens the case for a new class of structure, supervoids, not just the expected bubbles in the foam. These are cavernous chambers. They challenge the standard blueprint, so this comparative analysis reframes the mystery of BOOTES. It's no longer just a solitary oddity to explain away. It becomes a potential signpost, one of several, all pointing in the same direction, their collective evidence that the story of how the universe arranged itself is still being written. With chapters of profound emptiness we're only starting to read. We build universes inside supercomputers. They're not animations, they're mathematical models. You start with a digital soup, particles for dark matter and ordinary matter, spread across a virtual space that stretches with time. You give them the laws of physics as we know them. Gravity mainly, then you press play. The simulation runs for months, calculating the pull between trillions of particles over billions of virtual years. What comes out is a cosmic web, filaments, clusters, and voids. These digital universes, the Millennium Run, Illustris TNG, they've been successful. They reproduce the large-scale structure we see with remarkable fidelity, a triumph of modern cosmology. But there's a persistent problem. When scientists look for voids in these virtual cosmos, they find plenty. Bubbles of emptiness 100 million light-years wide or so, but they almost never find a void like the one in BOOTES, that staggering scale, that profound emptiness. It's an outlier. Their digital physics struggles to create it, so the researchers tweak the code. They adjust the starting conditions. They change the amount of dark energy. They modify the properties of dark matter. They amplify the initial ripples in certain ways. They run the simulation again and again. Sometimes a larger void will form. But to get one that truly matches the BOOTES void, they often have to push the parameters to extremes, to settings that don't align with our other observations of the universe. This difficulty is a clue written in ones and zeros. It tells us the great nothing isn't just rare, it's statistically challenging for our best models to produce. That leaves two broad possibilities. The first is that our universe simply rolled cosmic dice and got a once-in-a-billion result. We're the observers of a genuine fluke. The second possibility is more compelling. It suggests the physics in our simulations is incomplete. Maybe dark matter interacts with itself in ways we haven't accounted for. Maybe neutrinos, those ghostly particles, played a larger role in clearing out regions in the early universe. Or perhaps the initial seeds from inflation had a different pattern, a different texture than our standard assumptions allow. The silence of the BOOTES void echoes in these silent halls of supercomputers. Its absence in our digital worlds is as telling as its presence in our real one. It stands as a digital age monument to what we do not yet know, a quiet challenge from the real cosmos to our virtual ones, that immense silent sphere. It challenges our physics, but it also questions our place. For centuries, the human mind has grappled with nothingness, what it means to be truly empty. And the BOOTES void, this great nothing, makes that question real. It's not abstract anymore. It's a measurable, terrifying reality. Back in the 17th century, the philosopher Blaise Pascal wrote about this. He felt a dread before what he called the eternal silence of the infinite spaces. He looked at the stars and felt not wonder but a profound loneliness. A recognition of our own smallness, and that feeling finds its ultimate expression not in a sky full of stars but in a map showing a sphere where stars almost are not. That's the philosophical weight of it. We define the universe by what exists: planets, stars, galaxies. So what does it mean to encounter a region defined by its absence? Does that absence have its own identity, or is it just a blank space waiting to be filled? Some philosophies suggest nothingness isn't passive. It's not just a lack. It can be a positive force, a defining feature. It gives shape and meaning to everything else. Think of silence in music. The pause between notes isn't just an empty moment. It creates rhythm. It gives the sound that follows its impact. In that sense, the void is the cosmic silence, the vast pause. It's what allows the brilliant filaments of the cosmic web to have their meaning. It's the contrast that makes structure visible. Without these immense deserts, the crowded cities of galaxies would lose their definition. They'd blur into a uniform glow. So the nothingness of the BOOTES void might be essential. It's the negative space that completes the picture of the universe, that shifts our perspective. From seeing it as a problem to be solved, a flaw in the data, to seeing it as a necessary part of the whole, a feature of cosmic aesthetics. But this intellectual understanding doesn't ease the visceral feeling. The scale is inhuman. It speaks of distances so vast that human history is less than a blink. It reminds us we live on a fragile speck, orbiting an ordinary star. On the outskirts of an ordinary galaxy, which itself might be perched on the fringe of an ordinary filament. And beyond that filament lies an ocean of dark so large it defies comprehension. It can feel like a lesson in insignificance, but it can also be a lesson in rarity, and therefore in value. In all that staggering emptiness, here we are. On a world that teems with life, consciousness, and curiosity, we are the universe's way of looking back at itself, of trying to understand its own structure, even the parts defined by what is missing. So the BOOTES void is more than a scientific mystery. It's a mirror. It reflects back our own search for meaning in the face of the infinite. It asks us what it means to exist in a cosmos that contains such profound non-existence. And in asking, it makes the act of exploration, pointing our telescopes at the dark and asking why, one of the most profoundly human things we can do. The key is seeing what we can't see right now. Our maps of the cosmic desert are like sketches, twilight sketches. We know the major landmarks, but the finer details, the subtle contours of the emptiness, they're still hidden. To solve the mystery of the great nothing, we need new eyes on the sky, a new generation of instruments, something that can turn our sketches into a high-definition portrait. That's the Vera C. Rubin Observatory in Chile. Its mission is the legacy survey of space and time. For 10 years, this telescope will scan the entire southern sky over and over. Its camera is so large, a single image would need over 150 high-resolution television screens to display. It will catalog billions of galaxies. Fainter, deeper than anything before. For the BOOTES void, this is a revolution in detail. The Rubin will likely find thousands of dwarf galaxies, previously invisible ones, drifting in that vast expanse. The question is their pattern. Are they scattered randomly, or do they trace delicate structures, faint structures within the emptiness? This data tells us if the void is a simple, smooth bubble, or if it has a complex internal architecture. Ghostly filaments of its own, it will measure the void's boundaries with razor precision, the true sharpness of its walls. Then, looking deeper, there's the Nancy Grace Roman Space Telescope. Roman's power is peering through cosmic dust. It will perform ultra-deep surveys, seeing the faint glow of the earliest galaxies. This is crucial for understanding voids in time, not just space. By mapping galaxies at different cosmic epochs, Roman could show us how a void like BOOTES grew. Did it start as a small underdensity and inflate, or was it born large? It will look for the faintest inhabitants, galaxies so old and quiet they're essentially fossils from the early universe, preserved by their isolation. And from the ground, an entirely different sense comes online, the sense of hearing, the square kilometer array, the SCAR. It will be the world's largest radio telescope spread across 2 continents. It doesn't look for starlight. It maps the universe by detecting the faint radio signal from neutral hydrogen gas. Hydrogen is the raw material for stars. It fills the space between galaxies. The SKA will create 3-dimensional maps of this gas throughout the cosmos. For void studies, this is transformative. It lets us see the void not just by the galaxies that are there, but by the gas that isn't. It can measure the precise density of intergalactic material inside the BOOTES void. Is it a perfect vacuum, or is there a thin, uniform mist of gas? The answer tells us if the void was cleared out completely, or if galaxy formation simply failed to start there. And by mapping the hydrogen in the galaxies that do exist inside the void, we can measure their rotation and motion. Incredible accuracy. Are they drifting aimlessly or flowing along some unseen river within the emptiness? This coming flood of data changes the game. It moves us from studying a single strange object to doing rigorous statistical cosmology. With Rubin and Roman finding potentially hundreds of new supervoids, we can finally build a proper census. How common are these giants? What is their true size distribution? This provides the hard numbers to test our theories. Does the number of BOOTES-sized voids match the predictions of the standard model, or does it demand something new? Early dark energy, modified gravity. The data allows for precise tests, measuring the subtle gravitational lensing effects of these vast empty regions on the cosmic microwave background. Probing their total mass, their connection to the cold spot, we're at the edge of a new era. The great cosmic deserts are about to be mapped with a clarity we've never known. The silence of the BOOTES void will soon be filled, not with stars but with data, and in that data we may finally hear the echo of whatever created this profound nothingness in the first place. That profound emptiness gives you a kind of clarity. Astronomers have started to see the BOOTES void as a tool. It works like a cosmic time machine. It gives us one of the clearest windows we have into the early universe. And the reason is what's missing. When light from something incredibly far away, one of the first galaxies, travels toward us, that trip is usually turbulent. It goes through the crowded filaments and clusters of the cosmic web. In those dense areas, the light gets bent. Its path gets distorted by the gravity of matter in the way. That's gravitational lensing, and the light gets scattered. It gets absorbed by clouds of gas and dust between galaxies. It's like trying to see a distant lighthouse through a storm. Through fog, the image blurs, the signal gets muddled, but then imagine that same beam of ancient light. On its 13 billion-year journey, it passes right through the BOOTES void. For hundreds of millions of light years, it's moving through almost nothing. There's very little matter there to lens it, to bend its path, almost no gas or dust to absorb the photons. To scatter them for that long stretch, the light travels in silence, pristine silence. It's like the beam has entered a clear tunnel, a still tunnel through the cosmos. And that gives astronomers an exceptionally clean sightline. When they point telescopes through the void toward the distant universe on the other side, they get a less corrupted signal. They can see the faint glow of primordial galaxies, the brilliant cores of early quasars. They see them with a clarity that's unprecedented. It's the difference between looking through clean glass and glass that's frosted. Warped, that practical utility changes the great nothing. It stops being just a mysterious absence. It becomes a strategic asset, a natural observatory. By using the void as this clear corridor, researchers can probe the infant cosmos. They can see it in finer detail. They can test models of how the first stars ignited, how the first galaxies formed in the darkness. They can measure the properties of the intergalactic medium from a time before the void even existed. So a cosmological problem turns into an opportunity. The very thing that made the BOOTES void so puzzling, its staggering emptiness, is what makes it invaluable. It lets us separate the effects of the distant source itself from all the noise in between. The void becomes a lens of pure transparency, a silent guide. It helps us see further back in time, with sharper eyes than we ever could through the bustling streets of the cosmic web. Its greatest gift might not be the answer to its own origin. It might be the clearer view it gives us of everything else. There's this long-standing debate in galaxy evolution. Nature versus nurture. Does a galaxy become what it is because of its own internal physics, its nature, or is it shaped by its environment, the neighborhood it grows up in, its nurture? For decades, you couldn't separate the two. Galaxies in clusters are constantly influenced, harassed, stripped of gas, merged with others. It's a bustling, chaotic city. But the BOOTES void changes that. It offers the ultimate control group, a place where nurture is almost absent. Here, galaxies grow up in profound isolation. They're the cosmic equivalent of children raised in complete solitude. And by studying them, you can finally see what a galaxy's true nature looks like. When it's left entirely to its own devices, detailed surveys of the void's few inhabitants have started to show things. The first clue is star formation. In the dense filaments of the cosmic web, star formation is often a violent, triggered event. A galactic collision sends shockwaves through gas clouds, igniting bursts of new stars. But in the void, without those collisions, what happens? The data suggests these isolated galaxies often have unusually low but steady rates of star formation. They aren't experiencing dramatic bursts. They're quietly, slowly converting their internal gas reserves into stars over eons. It's a gentle simmer, not a roaring fire. That tells us the wild starbursts we see elsewhere aren't an inherent part of a galaxy's life cycle. They're a direct result of environmental nurture, of cosmic crowding. Then there's their shape. In crowded regions, spiral galaxies are often distorted. Their beautiful arms are pulled out of alignment by gravitational tides from passing neighbors. Some are completely transformed into featureless elliptical blobs by major mergers. But the spirals in the BOOTES void show a different story. They tend to be remarkably regular. Symmetric, pristine, their spiral arms are undisturbed, winding gracefully around their cores. That pristine structure suggests the classic, majestic spiral might be the default, natural state for a certain type of galaxy. It's the state it maintains when left alone. The twisted and elliptical shapes we commonly see are largely the scars of a violent environmental history. They're the result of nurture. Perhaps the most subtle clue comes from chemistry. Galaxies aren't closed boxes. In rich environments, they exchange material. When massive stars explode as supernova in one galaxy, their metal-enriched winds can pollute the intergalactic medium, eventually be absorbed by a neighboring galaxy. That external enrichment is a form of cosmic nurture. It changes a galaxy's chemical makeup, but a galaxy in the void has no neighbors. It can only enrich itself with the elements forged in its own stars. Studies of the chemical composition of void galaxies show they often have lower overall metallicities. They're more chemically pristine. That confirms they've lived a sheltered life, never receiving an infusion of processed material from the outside. Their chemistry is a pure product of their own internal history. Each of these observations turns the BOOTES void from a curiosity into a fundamental laboratory. By comparing a void galaxy to an identical-looking galaxy in a cluster, astronomers can subtract the effects of environment. they can ask, what traits remain when you remove all the noise? The answer is rewriting the textbooks on galaxy formation. It's helping to disentangle the impossibly complex web of factors, the things that turn primordial clouds of hydrogen and helium into the diverse galactic ecosystems we see. The profound silence of the great nothing, therefore, isn't just an emptiness to be explained. It's the pristine condition required for a perfect experiment. In its quiet dark, we're finally hearing the universe's answer to one of its oldest questions. What is the true, unaltered nature of a galaxy? The BOOTES void isn't just in the science journals. It's gotten out, it's moved into culture. The idea of this great nothing, this huge cosmic desert, it hits something in people. It connects to old fears and to modern interests. You see it in those science documentaries. The narrators get quiet talking about this abyss. Shows like The Universe have done pieces on it. They present it as a major cosmic puzzle. The visuals are strong, a simulation where you're flying past galaxies, and then you just drop into this dark, empty sphere. It swallows the light. It's a visual for the unknown, and it grabs people. It goes into fiction, too. The void is a blank slate for stories. In science fiction, it's the place for isolation, for cosmic horror, a generation ship lost in there for thousands of years. The crew forgets why they're even there, or some ancient thing sleeping in the dark that plays on a basic fear of the void. The emptiness isn't just a backdrop. It can be a character, a silent pressure that works on an explorer's mind. These stories take the astronomy and turn it into narratives about being alone, about enduring, about hitting the edge of what we can know. Music's been influenced by it. There's an experimental band, The Caretaker. They did an album called An Empty Bliss Beyond This World. It's not directly about the void, but it's about memory dissolving into nothing. The link is there in the sound, in these ambient, drifting pieces that feel like vast, quiet space. So the void enters culture as a feeling, a mood, and that echo goes way back. Look at creation myths. So many of them start with a void, a formless chaos, the Greek idea of chaos, the Norse Ginnungagap, that yawning gap, the Taoist idea of undifferentiated potential. Before something, there was nothing. These aren't science, but they're human answers to the same question the BOOTES void poses. What's in the absence of everything? That parallel means something. It shows that our science and our myth-making come from the same place, a deep curiosity about where we fit. The BOOTES void is a modern discovery. But the awe it creates is ancient. It gets into the public mind because it gives a real, measurable shape to that old concept of the abyss. It turns a statistical anomaly into a story. A story about wonder, about the fear of being insignificant, about wanting to find meaning even in total silence. So the great nothing becomes more than something to study. It becomes a mirror. It reflects this ongoing conversation we have with what's vast and what's unknown. With a mystery this deep, confusion is natural. So it helps to say what the BOOTES void isn't. First, and this matters most, it's not a threat. It's not some kind of cosmic predator growing to swallow our galaxy. The emptiness itself isn't pulling things in. It's just a place where there's very little matter. Our Milky Way sits inside the Laniakea supercluster, which is full of structure. We're millions of light years from the void's edge. The universe is expanding, so the distance between these large structures increases, but that doesn't mean the void is chasing us. It's a feature of the landscape. It's not a force moving through it. Second, it's not a perfect vacuum. When we say empty, we mean by astronomical standards. The space inside still contains the intergalactic medium, a thin haze of hydrogen gas. It contains dark matter, though much less than average. And as we know, it contains those few dozen lonely galaxies. Calling it a void is a relative term. It's compared to the crowded filaments nearby. It's profoundly underdense, but it's not completely devoid of all things. Third, its existence doesn't disprove the Big Bang. You might see such a huge hole and think it contradicts the idea of an expanding universe from a dense beginning. But the BOOTES void is actually a puzzle within our current cosmological framework. It's not evidence against it. Our models of the Big Bang and cosmic inflation predict variations in density. The void is an extreme variation. It challenges the details of those models, but not their foundational principles. It asks us to refine our understanding of how structure forms. Not to throw out the entire story. Finally, while speculation is fun, the void isn't compelling evidence for alien megastructures or cosmic engineering. That idea is a fascinating thought experiment. It shows human imagination facing the unknown, but scientifically, there's no data to support it. All the void's observed properties, however extreme, can be discussed using known physics and cosmology. The leap to a technological cause is enormous. Without any empirical signal, it stays in the realm of creative fiction. Clearing this up is important. It separates established, testable science from sensational speculation. The real wonder of the BOOTES void isn't invented dangers or far-fetched myths. It's the genuine, profound mystery it presents to our current understanding of the cosmos. Its silence asks real questions about gravity, dark energy, and the seeds of the universe itself. And that reality is far more intriguing than any fiction. Dark matter builds the universe's structure. It's this invisible framework galaxies form along it. We can't see it directly, but we see gravity's effects. It shapes everything. It pulls normal matter into place. So when we find a place like the BOOTES void, this huge empty space, the question changes. Is it empty because the dark matter is gone? Or is the dark matter there but just arranged wrong? That difference matters. In the standard view, dark matter is cold. Its particles moved slowly early on. That slowness let it clump. It formed dense halos. Those halos pulled in gas, hydrogen, helium. That gas collapsed into stars, into galaxies. It's a partnership. Dark matter sets the stage. Normal matter builds on it. Now imagine the BOOTES void starting out. If the dark matter there was smooth. A diffuse haze, not sharp clumps. The result would be quiet. The gravitational pulls would be weak, too shallow. The gas would never feel enough pull to collapse. To ignite, the region would stay empty, a vast underdense expanse. The dark matter would be present but faint, like a weak sketch that can't guide the paint. That leads to other ideas. What if dark matter isn't perfectly cold? Some theories say warm dark matter. These particles moved faster early on. That extra motion has a smoothing effect. It stops dark matter from forming the smallest clumps. It damps out tiny fluctuations. On the largest scales, the cosmic web still forms, but within it, voids could get larger. More pronounced, the BOOTES void's emptiness might be a sign of this warmer, more mobile dark matter. Another thought, dark matter might interact with itself. Not just through gravity, but through some other force. If particles can collide, scatter off each other, that transfers energy. Over billions of years, it could smooth out dense concentrations. A massive halo at the void's center, if one was there, might have evaporated from the inside out. Its particles scattering into a uniform cloud. This self-interaction could erase the seeds for galaxy formation, leaving a smoothed-out, barren region. So studying the BOOTES void probes the invisible majority by mapping the few galaxies inside it, by using gravitational lensing to trace the total mass seen and unseen. Astronomers can infer the dark matter's layout. Is it concentrated in faint halos around those lonely galaxies, or spread in a nearly uniform sheet? Each possibility tells a different story about dark matter's behavior. The great nothing becomes a natural experiment. Its extreme conditions test our understanding of the hidden framework. If the void's emptiness comes from an odd dark matter distribution, then its silence isn't an accident. It's a message about the character of the most dominant form of matter. Solving the mystery of what isn't there may depend on understanding the intricate behavior of what we cannot see. A star and its planets, that's where it starts, our solar system, a little neighborhood, and that neighborhood is inside a city, the Milky Way galaxy, hundreds of billions of stars. But galaxies, they're usually not alone. Ours is in a group, the local group, dozens of galaxies, all held together gently by gravity. That group is like a suburb. And then you have the cluster, the Virgo cluster, that's over 1,000 galaxies, a real metropolis, and clusters, they gather too, they form superclusters. Our local group is part of one, the Laniakea supercluster, a continent of galaxies, hundreds of millions of light years across, all flowing toward one center. A gravitational center, and these superclusters, they're not just blobs, they're the nodes, the dense knots in a pattern, a much larger pattern. They connect to each other. Through bridges, long, thin bridges of galaxies, filaments, they're like highways, the cosmic web, tracing the lines of dark matter. And between these filaments, between all that light and crowding, there are the voids. Huge spherical chambers, almost empty, that's the top of the hierarchy. After planets, stars, galaxies, groups, clusters, superclusters, the largest structures. In the observable universe, there are these voids, the BOOTES void. It's a supervoid, one of the largest chambers. In this cathedral, to picture it, think of a sponge. The solid part of the sponge, that's the filaments and superclusters, where the matter is, where the light is, and the air pockets inside, those are the voids. The structure needs both. The voids aren't accidents, they're not afterthoughts, they're the negative space that gives the positive space its form, its meaning. They were carved out by the same gravity that built the clusters, so studying a supervoid like BOOTES for astronomers, that's not a side project. It's fundamental, it's cosmology, reading the full blueprint of reality, to understand why the universe looks the way it does, from the spin of a planet to the flow of superclusters. You have to account for these great nothings. They're the silent features, the dominant ones in the architecture of everything. Our best map of the universe is the lambda cold dark matter model. It fits so much data from the background radiation to where galaxies are. But every map has its edges, places where the terrain doesn't match the chart. The BOOTES void is one of those places. Its scale, its emptiness, it's right at the boundary of what the standard model can comfortably produce. That tension raises a question. Is this just a rare but allowed feature within the known rules, or is it a signpost pointing to a different set of rules entirely? That's why anomalies matter. They're the cracks where new light gets in. Some researchers look at explaining such vast voids and wonder if the issue is gravity itself. The standard model needs dark matter to explain how galaxies hold together, how the cosmic web formed. But what if we've misunderstood gravity on the largest scales? There's an alternative called modified Newtonian dynamics, MND. It proposes gravity behaves differently when its pull becomes very faint, like at the edge of galaxies or in the deep emptiness of a void. In that idea, the modified laws could allow for larger, emptier voids to form, maybe with less dark matter or a different distribution of it. It's a radical rethinking. The emptiness becomes a direct clue to a fundamental force acting in a way we haven't codified. Other ideas look not at gravity, but at the dark components themselves. Maybe dark matter and dark energy aren't separate, inert things. Maybe they interact with each other over cosmic time. In these models of an interacting dark sector, the repulsive push of dark energy could have been stronger in the early universe in certain regions. It could have smoothed out matter, suppressed galaxy formation from the start, that could carve out primordial voids of exceptional size like BOOTES as a natural outcome. The void becomes less a statistical fluke and more a predicted consequence of a more complex, hidden physics. Now, these alternative frameworks face their own big challenges. They often struggle to explain other observations that the standard model handles elegantly, like the precise patterns in the cosmic background radiation. The lambda-cold dark matter model is still, by a wide margin, the best fit for the universe as a whole, but the persistent existence of outliers like the BOOTES void keeps these alternative ideas in active consideration. They're not replacements, they're important thought experiments. They represent different languages for describing the cosmos, and the void is a phrase each language has to learn to translate. So the great nothing acts as a profound stress test. It's a controlled extreme, a natural laboratory of absence where we pit our theories. Scientists will keep tweaking the standard model's parameters, running larger simulations, to see if within its flexible boundaries a void this vast can be born. If after all that it remains an uncomfortable outlier, its silence will grow louder. It could transform from a puzzle within cosmology into a cornerstone piece of evidence for whatever comes next. The void doesn't just ask what's missing from a region of space, it asks what might be missing from our story of everything. The BOOTES void is a canvas for artists. It's not just data, it's a source of inspiration. They face the same problem as the scientists: how to make something that vast, that silent, somehow real. But science uses math, art uses color, texture, sound. Digital artists create these visualizations. They're part map, part dream. You might see a single spiral galaxy. Just a tiny swirl of light, floating in a sphere of black so deep it feels like it's swallowing the screen. The scale isn't given in numbers, it's a feeling. A feeling of immense, crushing distance. Painters work with dark pigment, abstract fields, and in those fields, faint smudges of color. Those are the lonely galaxies. More felt than seen, it's isolation on a cosmic scale, a visual poetry of absence. Then there's music. Composers build soundscapes, long, sustained notes. Vast stretches of near silence. The music isn't about melody, it's about the space between the sounds. The emptiness becomes an active element, a low drone for the background hum of the universe. A single piano note repeated at immense intervals for a solitary star system. You don't just hear the notes, you feel the gulf between them. That captures the emotional weight. The awe, the slight unease the raw fact can inspire. This intersection matters. The data says the void is 330 million light-years wide. Art makes you feel what that means. It translates cosmic scale into human emotion. The existential wonder, that sublime mix of beauty and terror from confronting such a vast nothing. This creative response makes the cosmos accessible. Someone who'll never study a redshift survey can still connect with the discovery. They can stand before a painting, or lose themselves in a piece of music, and for a moment glimpse that profound silence. These artistic journeys remind us that science is a creative act too. Formulating a theory about the void's origin requires imagination. Visualizing its structure requires intuition. The artist and the scientist are both trying to comprehend the incomprehensible. They're using different languages to describe the same profound reality. By appreciating the art born from the BOOTES void, we engage with the mystery. Not just as an intellectual puzzle, but as a human experience. It becomes a shared story of curiosity, a testament to our need to find meaning and even beauty in the great dark. But the BOOTES void might not be the largest. There could be bigger ones out there, huge empty spaces we just haven't seen yet, and the answer is probably yes. Our maps of the cosmic web are incredible, but they're not finished. They're limited by two things: depth and coverage. Surveys like the Sloan have given us a great 3D atlas, but it only covers part of the sky and only to a certain distance. Beyond that, our data gets thin. There are huge volumes of the universe where we only have a rough sketch or no data at all, so the search has to look to the future and to different ways of seeing. The best tool for finding the next supervoids isn't optical light, it's radio waves, specifically the faint signal from neutral hydrogen gas. Hydrogen is everywhere, it's the most common element, and it fills the space between galaxies. If you build telescopes sensitive enough to map this hydrogen in 3D, you can trace the cosmic web not by the galaxies, but by the raw material itself. Projects like the Square Kilometre Array are meant to do that. They'll take a census of the gas, showing the true structure of the cosmos, including the empty chambers, in incredible detail. And in that new data, scientists are looking for what they call ultra-large voids, regions that could be 500 million, even 1 billion light-years across. Voids so big they'd make the BOOTES void seem like a modest pocket of space, but finding one isn't just about spotting a big empty spot. It's a technical challenge. Where does a void actually end? Defining the boundary of an underdense region in a fuzzy 3D map is hard. Is the wall sharp where galaxy counts just drop off, or is it a gradual fade, a gentle slope into nothing? Cosmologists use statistical methods for this. They run algorithms that define voids based on local density and compare them to thousands of simulated universes to see if a candidate is truly exceptional or just normal variation. And the search for the largest void is more than a record book. It's a test of our models. Every new candidate, every potential champion, pushes against the predictions of our standard cosmology. If we start finding multiple voids much larger than BOOTES, that would be a strong signal. It could mean the initial conditions of the universe were more extreme, or that something like early dark energy played a bigger role in shaping things. It would mean the cosmic web isn't just complex, its contrasts are more extreme than we ever saw from our limited view. The silence we've been studying might just be a prelude. A deeper, more profound quiet, still waiting in the dark. That emptiness has a story. It has a biography written in expanding space, a void like the one in BOOTES. It wasn't born fully formed. It started as a whisper, a faint dip in the density of the early universe, just a region where, by chance, there was a little less stuff. At first, that didn't matter. But as the cosmos kept expanding, that tiny seed had a different destiny. The key is gravity, or the lack of it. A region with less matter has weaker gravitational pull. It can't hold itself together as tightly. So when the universe expands, this underdense patch expands faster than the crowded areas around it. That's void expansion. And it's a runaway process. As the void grows, it gets emptier relative to its surroundings. That weakens its gravity further, lets it expand even faster. It's a self-reinforcing cycle. Over billions of years, that faint seed gets stretched into a colossal spherical chamber. Galaxies that might have been there get pulled toward the denser walls. They're siphoned away, leaving a deeper silence. The void doesn't push things out. It just fails to hold on. What we see in BOOTES is its mature phase. A stable bubble in the cosmic web, but its story isn't over. We have to look ahead to a future shaped by dark energy. As this repulsive force becomes dominant, its effect on voids will be profound. Voids already expand faster than average. With dark energy, that expansion accelerates. They bloat at an ever-increasing rate. Their boundaries get sharper. Their interiors more desolate, and as they grow, neighboring voids begin to touch. Their walls, those thin filaments of galaxies, they stretch and finally rupture. Like soap bubbles merging, these voids coalesce. The BOOTES void may one day meet another giant. They'll fuse into a single, incomprehensibly large expanse of nothing. This process continues. Over time scales that dwarf human history. Voids merge into supervoids. Supervoids merge into gargantuan void complexes. The brilliant filaments and glittering clusters of the cosmic web get stretched apart. Isolated on islands in a growing sea of dark, the universe's large-scale structure simplifies into a vast, dilute foam where the empty spaces are the rule. Not the exception, that's a possible end to the story. A cold, quiet, isolated expanse. So the BOOTES void is more than a relic. In its silent growth, we see a microcosm of the universe's own far future. It's a harbinger, a preview of a cosmos where expansion wins, where structure fades, and where the great nothings become the defining feature of all that is. The best place to learn about the cosmos might be where there's almost nothing, the BOOTES void. It's more than a mystery for astronomers. It's a story that teaches the fundamentals of science. It turns abstract ideas into real questions. You can start with scale. Have students calculate the volume of that sphere of emptiness. Compare it to the volume of our local supercluster. The numbers are staggering. They force you to confront the true size of things. That exercise makes cosmic scale personal, unforgettable. From there, the void shows the large-scale structure of the universe. You can show a map of the cosmic web, the bright filaments, the crowded nodes, and then you point to the dark bubble. That visual makes the concept immediate. It shows that structure isn't just about what's there, it's also about what isn't. The void becomes the negative space that defines the sculpture. Students can plot the few known galaxies inside it on a three-dimensional grid. Seeing how sparse those points are compared to a typical region of space, that drives home the meaning of underdensity. It turns a statistical term into a visual, emotional reality. Most powerfully, the Great Nothing is a masterclass in the scientific method. Here's a clear, observed fact: a huge, empty region. The data is solid, but the explanation is not. A teacher can present the competing ideas. Was it carved by an early collision between universes? Is it a gravitational sink, a frozen sound wave, or just a rare roll of the cosmic dice? Walking through each one shows how scientists build models. They start with observation. They propose mechanisms based on known physics. They make testable predictions. And then they look for new data to rule possibilities in or out. This process shows a crucial lesson. Real science often operates in zones of uncertainty. It's not a march from question to definitive answer. It's a conversation with the unknown. The BOOTES void, with its unresolved mystery, shows that science is alive. It's a dynamic, iterative process of inquiry, not a static collection of facts in a textbook. Engaging with it encourages critical thinking. Students learn to weigh evidence, to understand that multiple explanations can coexist until one is strongly favored, to be comfortable with not yet knowing. Simple classroom activities bring this to life. Students can use redshift data to estimate the void's boundaries. They can research and debate the different theories, each team advocating for a different origin story. They can even try to design a thought experiment for a future telescope. What single observation would they make to test their favorite idea? This kind of engagement does more than teach cosmology. It inspires a mindset. It shows that looking at the sky and asking what's missing is just as important as cataloging what we see. It invites the next generation to not just learn the map of the universe, but to wonder about the blank spaces still waiting for their names. Our world takes up the whole frame, the rhythm of our days, the personal challenges, the small triumphs. It all feels immediate. It feels real. It's our entire universe. Then you hear about something like the BOOTES void, a sphere of cosmic quiet, so vast it could hold thousands of galaxies like ours, and yet it holds almost none. That knowledge does something. It pulls the camera way back, not just to a city view, not just to orbit. It pulls it outside of time, outside of human concern. It's the ultimate wide shot, and in that frame, our individual stories, our histories, even our civilizations, they become these vanishingly small points of light. Just points in an incomprehensible dark. That realization can be humbling. It can stir a kind of cosmic loneliness, a feeling that our struggles are insignificant against that backdrop. Against that eternal silence, that feeling is real, it's ancient. Philosophers and poets have grappled with it for millennia, but there's another side to this. The very act of feeling that awe, of recognizing that scale, that's uniquely human. The stars don't wonder about us, the void doesn't contemplate itself. We do. This capacity for reflection, for asking questions that reach beyond our own horizon, that's our defining gift. The BOOTES void isn't just out there. It's also a mirror. It reflects back our own tiny, fragile, brilliant place in the order of things. We are the part of the universe that has become self-aware. That can map the emptiness and give it a name. That can feel wonder in the face of it, and that shifts the perspective from insignificance to a kind of rare privilege. In all that sprawling cosmic architecture, across billions of years and light years, we are the point where the universe begins to understand itself. The anxiety of scale, it melts into a profound curiosity. Our problems don't become less real, but they get framed within a grander, more mysterious narrative. The same curiosity that drives an astronomer to chart the void, that's the same spark that drives us to solve problems, to create art, to connect. It's the impulse to reach beyond our immediate circumstances, to touch something larger. So contemplating the great nothing, it's not an exercise in despair, it's an invitation to expand our sense of what's possible. It teaches humility, yes, but it also teaches ambition. The ambition to keep looking, to keep questioning, to keep building tools that let us see further. Our ability to detect this void, to measure its staggering dimensions, to debate its origins across decades, that's a monumental human achievement. It's a story not of our smallness, but of the reach of our collective mind. So the next time the weight of the world feels heavy, remember the void. Let its silent expanse be a reminder that we are part of a story far grander, far more mysterious than our daily view allows. And in that vastness, our curiosity is the most significant light of all. The search for the great nothing. It's created tools that can see far beyond the cosmos. That's the hidden legacy of this work, a story of connections you wouldn't expect. To map an absence, you need a precise language for shape. That language is mathematics. It's topology. Topology studies the properties that stay the same when you stretch or bend something. To a topologist, a coffee mug and a donut are the same thing. They each have one whole, so when cosmologists look at the cosmic web, they use these concepts to define what a void even is. Is it a simple bubble or a complex tunnel system inside that filamentary structure? Then there's network theory, another framework. It describes the cosmic web as nodes and connections. The voids are the empty spaces in that network. And the algorithms made to find these voids, to classify them, they've turned out to be incredibly versatile. They're almost identical to the algorithms in medical imaging. When a radiologist needs a computer to find a cavity in a lung scan or a pocket of fluid in brain tissue, the software is solving the same basic problem. It's differentiating a region of low density from a field of higher density. So the cosmic search for emptiness directly improves how we diagnose the human body. The influence goes into economics and finance too. The statistics of extreme events like a market crash or a catastrophic flood, they rely on understanding the tails of probability distributions. A cosmic void is the ultimate statistical outlier in the distribution of matter. The mathematical techniques cosmologists refine to ask, how likely is a void this empty, are the same tools a risk analyst uses to ask, how likely is a loss this severe. By studying the rarest things in the universe, we get better at modeling the rarest, most impactful events here on Earth, and the philosophical engagement continues. It moves from awe to rigorous thought. The void challenges concepts of nothingness, existence, observation. It fuels debates in metaphysics and epistemology. This cross-pollination is the real power of fundamental research. We pointed telescopes at a dark patch of sky with a simple question: why is this so empty? In seeking the answer, we didn't just learn more about the cosmos. We developed sharper mathematical lenses, more sensitive diagnostic algorithms, deeper statistical models. The investigation into one cosmic mystery built a toolkit that now helps heal and protects and deepens understanding across human knowledge. The Great Silence has a very loud echo. The data from telescopes is this huge, unexplored ocean. Every major sky survey, from the Sloan Digital Sky Survey to the upcoming Legacy Survey of Space and Time, it captures images of billions of objects. And that creates an immense challenge for astronomers. They have to sift through all of it to find the subtle patterns, the rare anomalies, the things that hold the keys to cosmic mysteries. And that's where the human eye and mind become an indispensable tool. You don't need a PhD to help map the great nothing. You just need curiosity and an internet connection. Projects like Galaxies started this. They show volunteers images of galaxies from these massive surveys and ask simple questions. Is this galaxy a spiral or an elliptical? Are its arms tight or loose? That act of classification, done by hundreds of thousands of people, it creates a human-verified catalog. Algorithms can't match that nuance. For void science, this public effort changes everything. By classifying millions of galaxies, citizen scientists help build a sharper map of the cosmic web's filaments and walls. And that defines the voids between them with greater precision, but it goes deeper. Within the sparse population of the BOOTES void itself, there might be galaxies with strange, distorted shapes. Signs of a history shaped by isolation. A volunteer scrolling through images could be the first to spot a truly peculiar galaxy drifting in that desert, flagging it for follow-up. Other platforms are taking this further. Some projects invite the public to scan survey data targeting known void regions, searching for faint, diffuse smudges that could be uncatalogued dwarf galaxies or lonely star clusters. The human brain is good at pattern recognition. It spots subtle irregularities that computer algorithms are programmed to ignore. Every new galaxy found in the void, no matter how faint, adds another data point. It helps answer whether the void is uniformly empty or has a faint, underlying structure. By participating, you become an active partner. You're not just learning about the mystery, you're helping to solve it. This collaborative model accelerates research, but it also builds a connection, a personal connection between the public and the cosmos. The BOOTES void stops being a distant, abstract concept. It becomes a frontier where your own observations from your home computer contribute to a global understanding. So the great nothing transforms from a subject for specialists into a shared human endeavor. It invites everyone to be an explorer, turning the awe of the universe into the tangible act of discovery. After this whole journey through the evidence, you come back to the choice. Is the BOOTES void a fluke or is it a feature? That distinction changes everything about how you see the universe. The case for a fluke is built on probability, on sheer size. Our observable universe is unimaginably vast. It holds maybe 2 trillion galaxies. In a system that large, starting from random quantum seeds, the statistics say something. Extremely rare events aren't just possible, they're inevitable. They have to happen somewhere. It's like finding a single, perfectly round, white pebble on a whole beach of gray stones. The odds for any one pebble are vanishingly small, but with enough beach you will eventually find one. The BOOTES void could be that 1 in a billion white pebble. Our unfortunate luck to be positioned right there to see it. In that view, its staggering emptiness doesn't tell us anything new about physics. It just reminds us that in a cosmos this big, even the most improbable arrangements will show up sometimes. The mystery isn't in the void itself, it's in our own surprise at finding it. Now, the case for a feature is more compelling to a lot of scientists. It argues the void's properties are too extreme, too telling to just be chance. Its scale pushes against the limits of our best simulations, and its potential link to other puzzles, like the cold spot in the ancient light, suggests it might be part of a larger pattern. A single fluke is one thing, but a fluke that also seems to whisper connections to other unsolved mysteries starts to look like a clue. People who hold this view see the void not as a random roll of the dice, but as a signpost. It points to a gap in our understanding. Maybe our models of dark matter or dark energy are subtly wrong. Maybe the initial conditions of the universe weren't as random as we assume. The void, seen this way, is a feature of a cosmos whose blueprint we haven't fully decoded. Its silence is the sound of our models straining at their seams. We don't know which answer is true. The weight of evidence hasn't tipped the scale, and that's exactly why the BOOTES void remains so vital. If it were clearly just a fluke, we might note it and move on. If it were clearly a feature of new physics, it would change cosmology overnight. Its power lies in the unresolved tension, the not knowing. That uncertainty is what drives the most rigorous science. It forces astronomers to build better telescopes, to run more detailed simulations, to question their most comfortable assumptions. The great nothing, by refusing to give up its secret, ensures it will stay at the center of our quest to understand the cosmos. It's a permanent question mark in the sky, and that question is what propels us forward. This great silence in BOOTES is not alone. It's part of a whole family of mysteries. We've mapped the universe's structure, but its ingredients are still hidden. Dark matter shapes galaxies. It's most of the mass, but we've never seen a particle of it. Dark energy is even more elusive. It's this force pushing everything apart, and we don't understand it. Then there's the question of existence. After the Big Bang, matter and antimatter should have cancelled each other out. But they didn't. A tiny asymmetry left a remnant, and that remnant became everything we see. All these puzzles are on different scales. The initial singularity, the moment of the Big Bang, is where our physics breaks down. And then there's the multiverse, this idea that our cosmos might be one bubble in an infinite froth. The BOOTES void belongs with these. Its emptiness is a mystery of structure and scale. And when you put it alongside the others, you see a pattern. Cosmology isn't a set of solved problems. It's defined by its questions. The void isn't an isolated oddity. It's one piece of a puzzle. Understanding its emptiness might tell us something about dark energy, how it accelerates expansion, or its formation might depend on dark matter in the early universe. And a breakthrough in particle physics, explaining matter's dominance, could reveal new processes that shaped the infant cosmos, processes that left voids behind as fossils. This view is crucial. It keeps us from seeing any one mystery alone. We're in a golden age of discovery. Each anomaly, from the faintest particle to the largest abyss, is a thread in the same tapestry. Pulling on one thread like the great nothing might just tighten our understanding of the whole picture. We end without an answer. We end with the question itself. And that's the point. We started with a fact, a sphere, almost nothing inside it, hundreds of millions of light years wide. We followed its discovery. A quiet thing in the data, it just kept being there. Every new observation confirmed it. We looked at the cosmic web, how galaxies usually form along filaments. And this great nothing, it shouldn't be there. It breaks that pattern. Then we looked at the possibilities, the theories, ancient quantum seeds, colliding universes. A gravitational drain, echoes of primordial sound. Each one is a different language, trying to describe the same silence, and we saw what this emptiness gives us. It's a laboratory, a clear window to look back, a mirror in a way for our own search. The origin of the BOOTES void, we don't know it. It's still a mystery. And that's its power. That's what it does. Its unresolved nature is a beacon. It calls for better telescopes, sharper simulations, bolder ideas. It's a frontier. A blank space on the map, and it compels us to go further. This pursuit, this effort to comprehend something incomprehensible, it's a testament to human curiosity. It reminds us the universe isn't obligated to make sense to us. It's stranger, more vast, more wonderfully puzzling than we usually let ourselves think. Carl Sagan said it, somewhere, something incredible is waiting to be known. The BOOTES void is one of those things, an incredible nothing, and it keeps inviting us to look deeper, to question what we assume, to embrace that feeling, the awe of not knowing.